Okay, now we've finished our 3 functions, and I want to explain now this statement here. Suppose we want to use these functions repeatedly, and we will. They're general purpose functions that are useful in Bernoulli Trials programs. So rather than including them in every Jupyter cell that you use, we can put them into a Python file and then call them every time you want to use them. The way to do that is to put these 3 codes into a cell, and then at the beginning of that cell, put this command, write file, bernoullifunds.py. This is called a magic command. It kind of goes outside the language to execute commands and execute things on the program itself. So if you execute this cell, you'll get this output writing Bernoulli Funds Pi, and then you can go back into your, it's not here, but I'm here. You can go back into your directory and you'll find out that it has actually saved that file into the directory that you're using. Okay, actually I didn't save it yet, so let's go ahead and do that. So I'll go ahead and execute this. And then go back and you can see that. There it is. So in order to use this function, you would simply, in your new cell that you use, you would simply put this statement, run bernoullifunds.py. Now, there's another way of doing this. You can save the functions in a Python file and then do import, but then you would need to put a prefix on all of the functions that you call from here. Later on we'll do that, do examples of that, but here, just to get things started quickly, we'll do it this way. So let's go down to the next code. All right, this code is the code from here, and this is the code to D. And what D is supposed to do, is this right? Yeah. What D is supposed to do is find the detection rate. Now, what does the detection rate mean? It means what percentage of doctors whose probabilities go bad are actually detected by the procedure. Now here we're going to get a detection rate as a function of K. This K is the place where the doctor's success rate changes over. So for instance, if the doctor's success rate changes over near the beginning of the trials, then you'd expect him to be more likely to be detected. So for instance, if he's only goes 10 trials with the probability P, and then goes another 90 trials with probability P1, it seems that it would be much easier to detect him than if he goes 90 trials with probability P and only 10 trials with P1. It's hard to tell that he's only been changed over for 10 trials with a P1. So that's what this is going to do. So what you're going to have to do is find the statistic for different cases. When the doctor goes bad after 1, goes bad after 2, goes bad after 3, etc. So that's what this is down here. Now let's go through this. So we generate an n by n matrix of Bernoulli trials having success probability P. So that's the null hypothesis. This is the alternative hypothesis. And these 3 are just in order to get your cutoff value, because you need to have a cutoff value in order to compare against to detect whether the doctor's gone bad or not. So here you take null hypothesis. Here you find his log probability vector. You find his log alt probability vector under the alternative hypothesis. You take the difference. So this is the statistic. You're sorting the result and plotting the result, and then you're going to take the 95th percentile of this, and that's going to be our cutoff. What this says is that people under the null hypothesis, doctors under the null hypothesis, 95% of them will not go over this threshold, so you'll only get 5% of null hypothesis doctors by selecting this threshold. That means there's going to be some false alarms, and you're allowing 5% of null hypothesis doctors for your false alarm. That's a large number, but this is just some place to start. We can always change this by changing the value of Q. So then here we run this threshold against these doctors. These are the doctors who actually do go bad at some point during the process. They go bad from 0 up to n minus d minus 1. Okay, so they may go bad from the start or after the first trial, etc., etc. Okay, then we're going to plot this as a function of k. As I said, as k gets larger, you expect the detection rate to go down. The detection rate should be largest when k is smallest. Okay, so let's see how that code works here.